which we name it as IDP. So this is Lisa, who is our interviewee. She also suffered from multiple sclerosis, which she had a low hand coordination and even totally shaking. And she constantly shakes when trying to bring food to her mouth. So based on the statistics, there are about 2.9 million people around the world who also suffered from multiple sclerosis, and just around 1 to 2% per 100,000 people in Malaysia. So for this multiple sclerosis, women are 3 times more affected compared to men. So for our target user for this assistive device is people who with multiple sclerosis, age between 16 to 60, for both gender, and have difficulty with coordinated arm action. So this is our benchmark available, which is Liquid and ObiRobot. As you can see, EasyFit and ObiRobot fulfill all the requirements for our user needs, but in some features, EasyFit are better compared to ObiRobot in terms of portability and utensil compatibility.
So this is our user needs and jobs to be done. As you can see, there are 4 main components which are guidance mechanism, simple adjustment, movement absorption, and utensil holding. So how does this device work to fulfill this user needs? First, the user will put the bowl in this designated area, and then they will scoop the food and bring the spoon towards the magnetic holder, and if it's metal or steel, it will directly attach to the magnetic holder, and if it's not, we will need to use a magnet. As you can see, there are 2 zones here, which are stable region and unstable shaker region. This unstable shaker region marks where the shaking will be worsening, and then this is where our device should be helpful. Next. Okay, this is our detail of design solution. The main components are magnetic holder and slot design. Magnetic holder is to prevent slipping, and the slot design should enhance the coordination. This design should be able to follow the compliance standard. Next. This is our function decomposition matrix. The first one is comfort and safety, as requested by the interviewee herself. She wants to have no body-worn parts device and also ergonomic design. The next one is portability and storage. It should be able to be foldable into compact form. And the last one is fitting with ease, where it should support utensil, partial hands-free operation, and enable easy food reach. Okay, as you can see here, most of the functions interacted with each other. Next. For the build of process, to support utensil, we need to have one utensil holder arm, one adapter clamp, and for extendable arm, we need to have one telescopic arm tube. For rigidity, we need to have one stable enough base platform and 4 non-slip rubber bands. Next. For the customizable height, we need to have one telescopic vertical tube, one hydraulic mechanism, and a few of flexible joining segments. And for portability, we need to have a few of foldable joints and one pouch. This is our design specification table. For enable easy food reach, it should accommodate different user positions and location, where the entering target should be 20 cm to 30 cm length without buckling. And for support utensils securely, it needs to prevent rotation and translation of unwanted shaking. And the alignment should be within the range of narrow angle range. And the entering target should be able to resist 5 Newton load, 5 degree, less than 5 degree of rotation, and less than 1 cm translation. And for partial hands-free usage, it should be rich enough to stay stable and must resist tipping or shifting for more than 5 Newton load.
Okay, this is our CAD design, which consists of base, ratchet mechanism, adjustable arm, loop growth built magnet, and telescopic rod. So for the design analysis for telescopic rod, the purpose of the telescopic rod is we can provide extendability, and the engineering target, the rod should withstand around 5 Newton of force. So the material that we use for the telescopic rod is aluminium, and the buckling coefficient, we assume that K is equal to 1 because of the the size and the material suitable for the magnet to withstand 5 Newton of force. Based on our calculation, the size of the magnet is around 2 mm and the material used is ferrite magnet. So this is our bill of material, which extendable rod, base and magnet holder. For extendable rod, the length must need to be around 20 cm to 30 cm. The diameter outer is around 4 cm. The diameter inner is around 3.5 cm and the material is aluminium. So for the base, we suggest around the length and the width is around 20 cm and the material used is aluminium with the rubber anti-slip at the bottom of the base. So and lastly for the magnet holder, the type of magnet is ferrite magnet with the diameter of 20 mm and the thickness is 3 mm. Yeah, I think that's all from us. Thank you.
6 minutes, 25 seconds.
Okay. Good. You're prepared for presenting at least. So you are within the time. Your presentation slides are quite nice. Clear to the font and stuff. So that's the plus. Right now I'm going to come to the bad things. All right. No, not the bad things. Just your design analysis. What's the purpose of your design analysis?
So basically there's two, which is there's computer and also for the magnetic holder.
Yeah, I know. But like this one, why you design for buckling?
Because the load will the more
Like this one, you're using like a column under compressor load. That's the Euler formula that you're mentioning there, the critical. Is that actually what it needs to be to design for the rod?
so your question is why
I don't think this is relevant. I don't think you design for buckling. Buckling is not an issue with your case here, especially with 5 Newton. Even if you use this, it won't buckle. Wood, it won't buckle. Forget the metal. Okay, so that's not the purpose. So what is the purpose of the rod here?
to extend.
Extend.
Extend to height preference of the user.
Okay, any other function for the rod? That's all. So basically you don't need to design for this then. You have to make it whatever. It's very straightforward. Just get a rod that goes from this distance to that distance. So not much design actually in here. Okay? The next one. Here again, the holder, what are you trying to design here?
So basically, our device is going to be called the utensil.
Okay.
So we use magnet. So based on our product, we want to know what are the size of
So
the
the
magnet.
spoon, any spoon here or just specific spoon you're going to
So
provide?
basically, you can use like the metal or steel spoon directly.
Yeah,
But if you have the
most of
ideas,
the things are stainless steel. How about the magnetic of stainless steel? Is it okay?
yeah. Just like for item material, there are non-hermetic magnets like wood or plastic. We provide like we provide a steel with an attached magnet. So the steel can be used with other material of utensil, just like we provide additional.
You design there the magnetic one holder, so that means your spoon it will be by magnet, right? No attachment.
If the utensils are non-hermetic, which is it's not going to be like a plastic or wood. We have like a additional sleeve with an attached magnet to attach with our magnetic field. But
Why don't you apply that one just for all? Why do you need magnetic and non-magnetic in that sense?
just that we want to give like our user option if they have like a steel spoon, so they doesn't need to use like the additional part, the additional sleeve. So they place the spoon and directly attach to the magnet.
Understood. So you have the other is not in the same one, so it's plug and play, so either the magnet or the other or both together in your design. The two fixing mechanisms are or and, like A or B or A and B.
Can you?
You have a magnet, right? And you have a fixation. If it is not magnetic, metallic, then you fix it, right? So in your design here, do you have both at the same time? Or if it is not magnetic, then I remove and I install the
Oh
fixation?
no, you just have to attach the utensil with the slip and you can just attach to the magnet. So the magnet are the fixed one here.
The magnet there and the other one?
The other one is a slip with an attached magnet. So you just like slot in the utensil to the slip.
Why this complication? Why don't have just the fixation, and if metal or not metal, just fix the thing there, done. Why I have to be fancy and put a magnet there?
Originally, our idea is to use the magnet to align the spoon with the mouth. So if we just put it there, we'll just
But how the magnet? How you control the magnet? The magnet is just to hold. That's a magnetic force. There is no control there that it will move this or that and so on, right? To control. Anyway, so this is like the idea. I don't know. You have to think about it. But let's go back to the design, for example. Assuming that you're using the magnet. So how you decide on the magnet? How you decide the magnet that it will hold the spoon, and the spoon when it is loaded, it will be held also? Did you calculate any magnetic force there?
yeah. So basically, we calculate the weight of the spoon and also like the standard weight of the spoon can be hold.
Okay.
So based on our calculation, it's only with 0.68 Newton, which is very small. But because we the safety margins is like maybe like this gap.
How come 0.68 Newton? Why you said the spoon only is 5 kg, 0.5 kg, which is 5 Newton. So the spoon is 0.5 kg. What is that 0.5 kg?
That is the mass of the spoon.
The spoon.
Yeah, so the 0.05 is the weight of the spoon, while the 0.02 is like the standard weight the tablespoon can
So
hold.
now make up 0.05. Is that how much is that? That's is the same as 0.5.
Oh no, this one is like we constrain the machine, the safety. So we consider so we develop our product that can hold up to 5 Newton. Even though like the spoon only weight around 0.68 Newton with the
So the spoon is 50 grams.
yes.
And you designed it for 500 grams.
Yes.
Okay, why? Because you're going to be in space. 10 factor of safety.
We're not sure about how many times of the safety measure, right? We are considering about maybe there's a gap between the magnet and the utensil. So we take it around 5 Newton.
Then if you will ask me big question mark about your design number, because you put that 5 Newton. Why you decided on that 5 Newton? Where did you get it from? In your design spec, you said it has to hold 5 Newton. Why 5 Newton?
Yeah.
Why? From where you get that 0.5 kilogram? If the spoon is 50 grams, the food is 20 grams, so I'm designing for 70 grams. Supposedly that's the biggest weight I can have on my structure. Why I'm putting my design spec for 5 kilogram? 500 grams?
For now, we want to take in consideration of the spoon, but in the future, this device can be hold, like a more bigger spoon with a more weight and more food can be hold.
So you don't have a design spec basically. You just okay, let's design and whatever, then you can fit anything in there. So not specific. That's why my design spec actually. And then after that, this calculation here. where do you get this force? B squared A over 2 mu? Where do you get that formula from?
It's a simplified version of the magnetic force formula. So the P is the flux and magnetic flux of the magnet. So we use ferromagnet and the dV is 0.2 Tesla. Before this we use magnesium magnet, but it's too big.
So what is the A you're trying to calculate?
The area of the magnet, like we want to know what the diameter of the magnet that can hold up to 20 Newton.
Okay.
So because of the force of Newton and also
Okay, so that means you fix the material, which is whatever that magnet it has the mu, and then you find the size of the, that's okay. Design point of view is okay, that part. Okay, so that's what it is expected actually. So now I know that I need a magnet from this material with this area of diameter or whatever. But my concern is about actually your design spec. Any other components?
for the design.
Yeah.
For the design, only for the time you
No, but you have in your material, you have many. The base. How did you design the base?
for the design is we assume the
No, assume. What is your user needs? Go back to user needs or your design spec? No? What are you? No, the design spec. Design target, whatever. Yeah, this one. So, support utensils securely, allow free usage, enable easy food reach. That's all?
yeah.
Okay? So, that support utensils securely, okay. But, so this one does to support the spoon, basically.
Yeah.
Okay. But if I don't do like, properly my base, so then I have the spoon, I try to move, fold the things, and then it will tip over. So that's okay from the design, right?
But also, there's also have like rubber ETC at the bottom.
No, forget the anti-slip. Because you have an arm, you have a magnet, all this weight, and their center of gravity will be somewhere here. So your thing you put there, you fold the thing, you move the spoon, and then it will tip over because the weight here is more than the weight of your base. That's okay with the user.
No.
So the food on the floor, whatever, everything.
It's just that we can calculate the specific need for the weight and the length of the piece.
Yeah, you have to do the balance that one. It should be actually one of the safety here. Either for that one, support utensil security, that's one, but it should be something else also, that it should not tip. Nothing here that it was about your thing tipping. Right. So first it has to be the base, I don't know, maybe the surface, like you said, maybe fix it. It has some sucking, whatever things, then it will be fixed. Right. So then it won't be wobbly. And then the center of gravity, like when you design like a car, you design whatever thing. You have to make sure that it doesn't tip. When it is loaded, when it is in an operation, it should not flip or whatever. Okay, that's actually important in your design. Especially like your heavy metals, you have all the bars, this. So then definitely you have the center. The reaction will be at the base. All the strength will be at the base. So maybe that's stability. See, stability there. You have a design attribute. So under stability it should be that one. Not the security is different from stability. Stability is this. It's stable. It's not like shaking, wobbling, tipping. That's the stable. So you have to add another thing for stability. Another engineering parameter, whatever it is, that it shouldn't tip, shouldn't whatever, I don't know, should be fixed, and then you add something else. Any other parts you have? Can you go through bill of material or bill of process?
For our bill of material, we only have three, which is the base and also the extendable
Bar. And the Holden one, the Holden mechanism for the spoon?
of the reaction
Huh.
of the slot.
Yeah, how the lock? How you make sure that the lock is good enough for the spoon and for when the spoon is loaded and stuff, then the latch is strong enough and holding all those things?
For the provider of the magnetic feedback.
No, the latch, you have a holding mechanism also, right? So how do I know this holding is holding? It will work, it will hold. How you design that one? Every part, basically, I'm not on too long already, but every part that you have there, you have to show how you selected that part. It's not like, okay, yeah, I have a hatchet here. See, like for the magnet, you said, okay, I'm going to use a magnet from this material, whatever, ferro, blah, 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 steel. Then, okay, this magnet, it comes in different, whatever, diameters, different. Then, I'm going to design for me, I have to hold this weight and stuff. What will be the diameter, the appropriate diameter from my design? That I started from that 5 kilogram or 500 gram or whatever that has to hold. And then I found, oh, this is the match magnet I need. That's kind of the design. Any other part similar to the magnet should be the same way. There's a design, engineer and target, and then I have to have some property or characteristic of the component, and then I have to derive that. Like that one, the diameter of the magnet. This one will be, I don't know, the length or whatever it is of the bar. The other one, it will be maybe the thickness, the weight, etc. of the base, etc. Right? Now, if you have a hatchet, also I have to design. If it has a special mechanism, what is the spec that I need to go? I need this kind of hatchet to hold this spoon that has this much weight. All right? You have to design it. You have to have some characteristics. So when you go, I need a hatchet with this 1, 2, 3, or one specific characteristic that you calculate, and the other you can fix, like the magnet. You fix the material, you fix the mu, then you found the area. Right? So you have to do all the parts like that in your bill of materials. Cannot one is like, I have a base and that's it. It's going to be steel. That's it. And dimension I will take 10 by 10, whatever, like that. No. It has to be all calculated. Okay? Otherwise, okay. I mean, you're like I said, still a little bit better. The first parts are okay. I think the user needs also, they match. Except one, I didn't like the, can you show the slide when you repeat the user needs too many times? I mean, for presentation wise, go back, down. No, I think the other way. Like it is. Support utensils. Stand bar, rigid base. What is this? Those should be the function, should be what?
For support utensils user needs.
Is it user needs? Function.
It needs to produce.
No, but this one, I mean, for me, it's not like a function. This one, this like you have basically, this is your bill of process in a sense, because you mentioned the component, right? It should not be the component. This one, I'm not in the bill of process anyway, and then it is repeated. Maybe it can be, but it should be like kind of the function here, because whatever the enable the component is kind of the same. Say support utensil holder. Support utensil, the spoon for. I'm not sure how that's the. Okay? So those are here. Rigid base, stable base platform. I mean, what is this? Base. You're talking about the base. So that's the component itself. So both actually combine as a component. Then this one, you should put the user need or the function that you are looking for from those three things. The orange one. Huh? The other can be one, and then it can be maybe two, like all the support utensil, whatever these things, 1, 2. Then they could be for, let's say, function 1. For whatever, like one that want to feed, whatever, function 2. The other one for stability, blah, 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 that's the stability function. is the base platform, the non-sleep, blah blah blah. That's for stability, etc. Okay? Then it will be clearer to understand. Because here you have, for me, it's both kind of enabler and enabler. Just the wording is different. All right. Okay. Yeah, that's actually what I was asking. I think the presentation is nice, clear, colorful, not much text there, a lot of image. It's nice. Okay? Okay? So work on your rearranging this. I'm not convinced on engineering target. I want to, you didn't give me a good answer, whatever, why you picked the 5 Newton, but from where it came. Right? You have to justify that one. These 5 degrees and stuff, I didn't see it in your calculation. Why you have it as an engineering target? The 1 centimeter also. I mean, no need now, but you think about it for your final presentation. Okay? So when I ask, I expect to have an answer if you keep the same number. Otherwise, you modify them, just the number that you need for the calculation of the problem.
If I may add about this rotation, less than 5 degrees, right? So the way you design it is like it's missing.
Yeah.
Right, and then because you otherwise need to have a separate sleeve, right? So this sleeve must like really match with your what do you call it? Slot. Yeah. So the slot is also the design is not there. If you see the typical spoon, it's not really flat, right? So how it would attach with your magnet? Your magnet is like a flat surface. So can it really pull with the amount of force that you slip itself? Okay, and then how you make sure that it doesn't rotate beside you?
It's not mentioned there in your design. How do you achieve that 5 degree and you will see? Okay? Alright. And make sure your design analysis is proper, like I said. The first one, I don't see why you have, when you have like this and this, how the buckling is occurring, I don't see it. Okay? Buckling is when you have compression, like this one, and I'm applying like this. So this one, it will go like this.
It's more untypical, like
Okay.
more rotation.
For columns, I think the case here, I don't think it has any buckling. Alright? Alright, thank you. You are only 4? Your group? One? Left. Oh, absent. I have left us. Okay.
Alright, next group.
This is group 7, huh?
Yeah.
Then group 5. Come on. Study that in the chat.
Ready? Okay, you have 7 minutes. Your time starts now.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to all of you. So today we are from Group Ibn Sina, and I would like to present to you our progress presentation for our ACL episode. Next. So to brief, our problem is about ACL, which is anterior cruciate ligament injury, and to brief that ACL is one of the main important part that help to stabilize the knee during the movement, and overstretching or tearing during activities such as sports or sudden movement like walking or jumping can cause overstretching and tearing, and this will cause the ACL to tear, strain, or broke, or what you call break. So our target user is 2, which is minor ACL strain and also partial tear. This both is target 1. Stage 1 and stage 2, which is both of them need bracing in solution. Next. Okay, so this is the stats. Mostly male, 93.1%. involved in ACL injury, and both of them, and in this figure 4, as we can see, a lot of them is related to non-sports, which is in daily life routine. They might cause, they might feel involve them with the ACL injuries, because over twisting and over bending is related also with the jumping and also walking. So daily activities also can cause ACL injuries. Next. So for our problem solution, the simplified one is knee cannot effectively bear body weight, and because of over twisting, they will cause sharp pain and also further damage to wrist increase. And then knee stress, which is slowing the healing and also interrupt daily functions. And then load stress, which is additional weight will increase the knee instability, and it will cause the first one, which is knee stress, and will give you pain. And then meniscus collision, which is one of the natural damper that has been created by God, which is if this meniscus is broken, it will prevent proper recovery. So our description of solution idea is we have 4 things, which is we want to prevent overbending and overtesting in the knee, and also we want to ensure that we have that knee stability during the post-injury, and we want to use it to have comfort, and also they can adjustable for their for our product. And the last one is we can monitor and to prevent overbending and overtwisting to happen in the future. Next. So this is the draft of our design, and as you can see, the user need is we want to reduce the distress, and then we want to support faster recovery by avoiding meniscus collision, and we want to minimize pain while walking, and then we want to prevent the overbending, and the last one is we want to provide stability. Next. So this is our benchmarking. As you can see, we compare it with 2 products. 2 is from the market and 1 is from our solution. Next. So this is the 3D drawings.
Basically, this is our CAD drawing. It's not completed yet, but this is the main structure of our design. Later on, we will add the short and global, adjustable tension cable, and so on. Next. Okay, this is function decomposition matrix. Our main objective is to achieve structural support, comfort and pain relief, motion control, and also user-friendly design. Next, this is build-out process. We want to achieve knee stability support, where we use metal lightweight rigid frame, fastener and connector, tie and cuff braces, and adjustable clamp hinge. So second, we want to prevent overbending. We will use adjustable light or tension cable, anti-rotation cuff, and mechanical hinge with roller. And then we want to achieve shock absorption. We will use spring lever system and also multi-shaft and holder. And then we want to reduce pain while walking. We will use ergonomic padding and fast soft action. And last, we want to achieve quick setup and adjustability. So we will use quick lock bucket system and also adjustable macro strap. Okay, next. Okay, this is our design structure matrix.
And then continue to design specification table. For must have, we must have knee stability during post-injury, which can minimize pain during walking or standing. And then we will prevent overbending or twisting. And lastly, we support recovery by avoiding meniscus collision. So our engineering target for knee stability, we are able to support weight of the patient, which is averagely 80 kg, and then we prevent overbending, which is the angle is between 0 and 90 degree. And lastly, we absorb the force, or we absorb the torque which is below than 500 Newton meter. And then for should have, we have adjustability and comfort, which is the material that we use is below 2.5 kilogram, which is very light. Next slide. And then the design analysis for rigid frame used to support the stability, and then potential cable in between the rigid frame to prevent overbending, and then the spring damper system to absorb all the impact from the patient. Next.
Hands up.
Okay.
It's my group.
Okay. Like the first group, your slide is not that good, right? Some very small letter, whatever characters, very tough to see. Even you read it mistakenly. Instead of feet, you read it fast. Anyway, and then you didn't practice. You didn't prepare. You worked like the groups from last Tuesday. You talked about the problem, blah, 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 and then when you come design analysis, you didn't have time, which is the main core, like the design analysis, this aspect, that's actually for 7% or 8% of the marks. Instead of 2%, you spend like your 5 minutes on that. Anyway, practice for your final round, especially for your showcase also, all right? You don't want to waste your time on simple things or things that they don't carry much weight, and the core thing of your work you don't show it. So that's actually your loss. All right. Now, I think you didn't do much of the comments we did in the proposal. But anyway, let's go through them. What is the problem?
The problem is the patient feel the pain, and then they cannot bend more than 90 degrees, and then they cannot walk properly.
Okay. So this is after pro injury, right?
Yes.
After the
Yes.
injury, this one.
Yes.
All right. Now go to your first slides. Why you spend 2 slides, 3 slides, which he spent I think 3 minutes, 4 minutes to talk to me about the ACL. The ACL, that's okay. This is, we're gonna design things for people that they have ACL injury, right? Which is 20% of them or whatever. And after the operation, they need a bracelet. But the bracelet, they have this problem, blah, 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 blah. That's what you should say. You don't talk to me about this, and it happened during sport, not sport, blah, 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 which is, you're not a doctor, you're not trying to prevent the ACL injury. That's for someone who wants to prevent the ACL injury. Before the injury even, that's the problem. What you presented here. You should say, for ACL, they go do operation, and this is after that. Now what is the problem with the current bracelet? Then I can see your problem after that. Understand? So your problem identification is not really suitable to what you solved actually. What you solved is the pro. You gave me all the info of happening, when the ACL happened or why it happens and blah blah blah. Okay? All right. So go to the next slide. See this one also. All this it should be just maybe one sentence like this, like ACL happened for this match, dual sport, not dual sport, and they need to go through operation to fix it, and this is the problem after that. All that in one slide actually. Okay, next one. This is actually the problem. This one is kind of important. This is what you want to prevent bending after that, to do this, to reduce stress, etc. Okay? So these, they look fine. My concern is later for your design spec. Okay? Now go. Here you have, let me go back. So we have, let's remember this. Insufficient support, knee cannot effectively bear the body weight. Additional weight increases knee instability. I don't know what additional weight from where coming?
Extra weight.
Huh?
When you walk or walking and
extra loops with you, those loops will.
Okay, that additional you can start. Okay, I don't know how, but anyway, okay, meniscus collusion prevents. So that's meniscus collusion. That's knee stress. Then the healing. So knee stress is coming from the load, coming from
the load stress.
So it's not the same as the load stress?
No.
No. Okay. And let's say over twisting, sharp pain, blah blah blah. Okay. All right. So let's go now to your design spec, the table. Okay. So here I want knee stability. How is the stability is measured by ability to support 80 kg?
So basically 80 kilogram is taken from the average BMI that we show you before.
Okay.
The status, the fact before that it is how many? Can you go to previous slide on the stats? So as you can see, the BMI is about 18.5 to 24.
No, it's fine.
Yeah.
No, go back. 80, let's say, okay, you came with, so your bracelet should support people that are 80 kgs of weight, right? Okay? But then, design spec. Okay. But here your user need is knee stability during what? Minimize pain during walking or standing. Is 80 kg the measurement for this? To minimize the weight, to minimize the pain?
It doesn't match. What it's trying to say is that it doesn't match your user need with your target.
Because he is able to support weight of patient with the 8 kg, which has nothing to do with the pain here. This is the structure. Your knee has to support this weight. So this one it can be, I don't know what is that, if you have any of the needs for that, okay? But I don't see any. So this one is like just to be able to support that weight, which I don't see, like I said, the link. That's one, okay? So you have to make, if you say pain, you have to give me an engineering target that actually measure the pain, that prevent the pain. What if maybe what the load that shouldn't cause the pain, whatever it was, but it tried to be something like that, not like the weight of the patient. The second one, prevent overbending or over twisting. And then you say anyways 0 to 90. So 0 to 90, which one is this one?
The knee one.
Yeah, the knee. 0, what is 0?
0 is this one.
This one, and 90, going back 90 degrees. So that's what? What is that one? That's the acceptable bending for the knee? For the injured knee. Even for after ACL, you can do that. Okay, I'm not sure, but anyway.
What is the angle for overbending?
Overbending, yeah.
Overbending is what is the angle?
The angle is more than 90 degrees. So they can withstand 0 to 90, but after 90 degrees they will have pain. More than that.
So your product can help
To support until 90 degrees.
So 0 to 90, they all have a lot,
So
so
until
it
90
shouldn't
degrees
go
they will
more
not.
than 90.
but you want to prevent overbending.
Yeah.
Yes.
Overbending is
Over the 90 degrees.
over the 90 degrees.
So like if you sit like this, okay. If you walk, okay. But you cannot like sit on the floor to eat or whatever, you know, or to do salat, you know.
Squatting, something.
If you do salat, you don't do sujood, basically. Okay, you don't go down, you don't bend, kind of. Anyway, that one is coming from the doctor or whatever, the standard, that 090. Is that what is mentioned, not overbending? Where did you get that 090?
Article, yeah.
Article that for ACL, the bender should be within this range. Okay? If you say so, then just in the report it should be there. Slow increment of 5 or 15, friction, what is that? Why the friction here? And what do you mean by 5 degree or 15 degree friction?
ACL also can cause, if you go fast, it also can cause you
friction? Friction mean or what? What is friction here? You wrote it and you don't know why you write that word.
I think there's mistake of friction.
So basically here, with a slow increment of 15 or 5 or 15. How come 5 or 15?
Until
Huh? 5 to 15, not all 15. Okay, so within that range. The increment has to be, I can go 5, but increment again by time, by I don't know how you will do that one, but anyhow, and limits the rotation less than 1, limits the rotation. It's like coding, you know. Your engineering target should be straightforward, like numbers, you know. For me to understand this is like, it's like program. I have a coded program and I have to figure it out, you know. And then less than 1, I think there, limits the rotation. Less, 5 degrees, withstand torque, up to 40 Newton meter. What?
Oh, okay, friction is less than 1. Limits the rotation less than 5 degrees and it can withstand torque.
MashaAllah, you couldn't make it like one in a line, everyone in line, in separate lines, so then it will be clear. So the first line will be range of motion 0 to 90.
Yes.
That's it?
Yes.
And then slow increment 5 to 15.
Yes.
Then third line, friction less than 1.
Yes.
What is friction?
Friction, we have temper, right? Temper there. And then those are not too fast or too slow. It is so nice and it can help the slowly increment to go further. Instead of later, if we doesn't have the friction, the slowly increment will go fast. I mean 5 degrees to go 5 degrees is not fast. So it will be slowly.
No, but why you have to specify the friction? The friction is what? Of the mechanism?
Yeah, okay.
That should be the design actually. Because you have your design number 5 to 15. So how are you going to achieve 5 to 15? Then you do, and then you find that the friction should be less than 1. I don't know. Maybe that's the calculation that it should be done. But you don't specify everything here. So from that one, I don't think that if it is related to the 515, then just one will be maintained. They are not. And then the other one limits the rotation less than 5 degrees. What is so the other one is like this, the bending. This one rotation like this. Okay. And then withstand torque up to 40 Newton meter. So torque like the knee will be like this.
Yes.
The torque coming from?
Torque coming from our twisting and also.
Okay, and that 40 Newton meter from?
Calculation is analysis.
Huh?
Is analysis.
How is that design analysis? This is engineering target here.
It is also based on the 80 kilogram itself. The 80 kilogram.
Then it's not, you don't put it there. If your 80 kilogram is your engineering target, then this one will be calculated. In my design analysis, it will be calculated. So I don't put it there. Here, just the starting point. Whatever coming in or deduce it, then it's not in the engineering target. All right. If, like we assume here. So this all we discussed before. I don't know why we're doing it again. So support recovery by avoidant meniscus. Support recovery by avoidant meniscus collusion. How you avoid meniscus collusion? First of all, how the meniscus collusion happened? When it happened?
It happened between the femur, this part and this
Yeah, but
part.
when? What caused it?
When it happens,
What
it happens
caused
when
it?
jumping and also walking. Yeah, both of them.
Okay, so how you came with the force then here to measure the meniscus collusion? You can force
So
absorb more
force
than-
absorb is our mechanical system, which can absorb 500 or more than that. So it can avoid the collision to impact first. So the mechanical will impact first rather than the
What
collision.
mechanical? The system.
The system.
We're talking about the solution.
Yes.
Yeah, but that one has nothing to do with the solution. It should not be solution based here. It should be problem based. So here, if you say avoid the meniscus, I have to know the meniscus collusion when it happened. If it happened for 500 Newton meter, then I should make sure that the load coming to the meniscus will be less than that, for example. Right. And then I design my system to be able to give that. So if the force, like say jump is 1000, then my system have to absorb 600 and then leave only 400 for the meniscus. That's the design how it should be done. But you don't put here like I want, so I put this. No. So you have to be, like I said, whatever it needs, you have to get, like I said, either from the doctor, from this case, from the literature, from something that they say for meniscus collusion, this is the acceptable load, so that it won't happen, or it won't be damaged, or whatever, it doesn't pain. Then I use that one as my engineer. And then I design my system, whatever the mechanism you said, in order starting from that, and then find then what is the spec of my whatever, the friction or whatever it is, that system that should absorb, or the absorber I think you have here, the lot or something like to absorb or something like that, the spring damper, right? So that one it should be actually. So when you say here force absorb, is that by the Springer damper system? It will absorb more than 500 Newton meter?
Yes, again.
The 500 Newton meter, the force absorbed more than 500. Who's absorbing the force? Is it your mechanism, your solution should absorb that?
Our solution.
Why absorb on 500? Or more than 500?
I think it's related with weight also. You want it.
No, but weight, how I decide if it is 80 by 1, that one it will be what? By 10, so 800 Newton. Huh? But here you said, by the way, force absorbed and then 500 Newton meter. Is 500 Newton meter, is that a force? What is the unit of force? Newton. Newton meter is torque. Moment, torque, whatever, right? So how come force absorbed more than a moment? So is it a force or a torque? Force. Again, like I said, this it should be based on whatever the acceptable force that for the meniscus not to have collusion. Right? You have to find it from the medical record or whatever, and then you have to make sure, let's say if from the 800 kilogram is 800 Newton, let's say, but the meniscus can only support 200 Newton, that means your system has to absorb the 600, and then let only 200 go to the meniscus. Then you put your target there, like you said. Force absorbed should be more, or the force for the meniscus should be only 200. Right? So then you subtract, so in the 600 you design your system to absorb the 600. So all the design target had to be there. That's my point is, all the groups, I think none had a decent engineering target. All the 10 groups. You don't understand what is the engineering target looks like, or you don't get them right. Anyway, so I'm not going through the other. Please go through the others and do them properly. Can we see some of the design analysis example? Just one example. So what are you designing here?
So we design the IC. The type is larger than curve. So the length is not length. The diameter is 20 cm, and the curve is 17 cm, which is this length is an average length for human that is weight 80 kilogram, and then the thickness is 2 centimeter. We use the material that we use is aluminum, and then we calculate the total volume and the volume to calculate mass, density times volume, and then we got just 1.1 kilogram, which is weight is not a problem for our design. Okay, for the stress that apply to the
Don't. What is the point here? What are you trying to design? I don't get it. You have your structure there. Go back to the previous slide. So you want to design this. What is this one? What you call this? Bracelet? What is it?
rigid frame.
Rigid frame.
Ah.
Okay. So you want to design the rigid frame.
Yes.
Okay? First of all, what is the engineering target related to this? The 80 kilo, is it the 80 kilogram?
80
The
kilogram.
weight, have to support the weight.
Yes.
Okay. Okay. Then, what you need to design here, you decided the aluminum, so you decided the material, okay? So I'm
Yes.
going to make it from materials, alright? So, what else you need to know about it? The diameter, the thickness, the length.
Yes.
This 2020 here, right? That's the length. And then the diameter to put here and here, right? Diameter here, and length, and the thickness of this one.
Of the
This one, the ring, the ring
yes.
in the sense. Okay? So how did you decide about those? The diameter you said, based on the average thigh, blah, 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 whatever. Okay? So that one actually should be kind of engineering target in a sense. But anyway, okay. Let's assume, so that is what is that diameter? 20 centimeters. Or 17.
20 for the upper part, 17 for the lower part.
The lower part.
Because
Okay.
lower part is
That's for average
smaller.
one, you have that one. So no design there, based just on whatever. Okay. How about the length?
the length also we take the average
What
length.
average?
Average height person.
Of a person, the leg, so from here to here you put 20.
Yes, because
How about the thickness? Okay, I'm
Yeah.
following. I'm trying to go around. So how about the thickness?
the thickness we try an area which is at first we try make it 1 centimeter thickness,
Okay.
but by
So
calculating
is
it,
that the design we asked you to do? If I follow your logic, what's the difference if it is 80 kg or 10 kg, the person? No involvement here of the weight. So why that's my engineering target, and then I go and design, I choose 10, 20, 30,
Oh.
and then I get that one. So,
because we think that 80 kilogram is the maximum weight.
But how? My point is, this one, this frame, if it is 80 kg or 60 kg, it doesn't matter because there is no kg involved in my calculation here. So it fits everyone actually in a sense. So I'm not designing for the 80 kg, so my engineering target is useless.
I think the 80 kilogram is because we said so. The design is not completed yet. Okay, so
But even if it is complete, how are you going to involve the
it
80
has one
kg here?
here, one structure here, and those structure will withstand the weight actually.
How is going to stand the weight? That one, you're not going to put your weight over
this
here.
one.
You just
Structure here until the feet. So those feet will help to
So that
withstand.
leg is not, the leg is not supporting the weight anymore.
This one is to prevent the overbending and over twisting.
Okay, now we're talking about different story. I'm talking about the weight.
Yeah, I know about
The waist of the bend is different. Okay, the waist is like this. You know, it has nothing to do with the weight in a sense. Okay, or with the movement. My point is whether I don't see again. My point here, if you decided on the 2, 17, 20, blah blah blah, so then you don't need an engineering target. You are very strong with the wahi, and you know what is the solution without even doing calculation. Okay, that's my point. So here, if you say like, okay, the 20 is from the average length, this from the average whatever diameter, at least the thickness has to be unknown and has to be related to the weight, that 80 kg, I don't know how it is involved, in order to find that thickness. Then I can see, okay, you did the design. So that thickness for 80. If I put 60, I'll find a different thickness. If I put 10 kg, it will be a different thickness. Then you're doing design based on your engineering standard. But when you fix everything, 80, no point. I just put it there for decoration. Alright? I didn't use it anyway. Anyway, I think no need to go for the other, but just you understand my point, I hope. All the component has to be the same. You cannot fix everything, or you do trial and error and see which one. Oh, this one, then it's okay. It can support 80 or it can support 60. No. You should start from that 80 and find one that it supports that 80. That's it. No trial and error. Okay? All right. This is group 5, huh? So can you, the slides for the next? I want to see the slides for the other design analysis. The next slide, Okay, next. Okay, that's all, huh? Please keep in mind, we don't want just to see some equation and numbers for the sake of equation of numbers. If I am not related to your design, no point of putting them. They will be actually against you, not for you. Okay? So better you leave it blank actually than put in, let's say, buckling when there is no buckling. Or put in, I don't know, this like frame where you didn't do any calculation related to the engineering target. Okay? Anyway, okay. Yeah, thank you, group 5. Keep in mind, if I am harsh or you think I'm angry, I'm not angry because I'm angry because you didn't all this lecture, all this discussion, and then looks like it's not going through you or to you. So maybe I'm angry on myself, not on you. But remember all the points, try to write them now. Take notes before you forget, and then you don't repeat in the final presentation. Hopefully the final presentation will be easier for you and for us. So just one or two questions, everything is clear, nice. Okay? Please take notes of the comments. I'm not doing it for the exercise.
Okay, ready? Your time, you have 7 minutes. Your time starts now.
Okay, Assalamualaikum all. So we are from Group 6, Universitas, supervised by the Rahman. This is the members, 2 of them are absent due to medical reason. Okay, next.
Is this a new one?
Yes.
Oh, so no more heat.
No. It's still located.
Alright, good. So from heat we went to the car. I don't know how, but go. Let's see.
Okay. What is our problem? So we have interviewed our interview, Mr. Kamal. Sorry for the blur. So after COVID, he is forced to be a driver or e-hailing driver. So he complained that his lower back is always have pain. So we can see the trend from 2017 to 2023. There is an increase in e-hailing service, and of course it wasn't post-pandemic. So what is our target reason? Who is our target reason? Is older workers B40 that have that which is e-hailing drivers, which in age group of 41 to 60. Okay, next.
Sorry, this group 2 or 6?
6. Okay, so what is our proposed solution? Policy drive. So this we will come up with policy drive to provide support, and also maintain pressure distribution, and also then have a vibration dampening from the material. So it is supported by Chong et al. That poor posture and exposure to whole body vibration is crucial factor to the lower back pain. Okay, next. So this is our benchmarking table. The left side we will focus on the lumbar support. This to top is for pressure distribution, and this to at the bottom is for vibration dampening. So basically we will combine all of them and put it in a car seat, which is also not very costly. Next. So this is just a graph of our CAD model, but we can visualize it by sorry for at least Mona is enrolled. So we will layer them with EVA from back, and EVA from back for vibration dependent, and also Okay, and then we will put on straps to make sure the posture is good enough. Okay, next. So this is our this design spec table. So we will solve provide manual support from the user needs. We translate to 10 to 15 Newton support, head adjustable 100 to 200 millimeter range. And also pressure distribution below 30 kilopascal. Vibration dampening effect by 50% at 4 to 8 hertz range. Next. Okay, we also make sure the polytrack is user friendly. We can only calculated the total weight and the only the total weight. Okay, next. Okay, so for design analysis, user need one relief. We target for the excessive force to be 10 to 15 Newton, which both qualify under 30 kilopascal. And then the lumbar height, this is from an article. Ceiling shoulder height should be 40% from the seat to the shoulder height. So the range is 102 and 98 and 8. So this connect. Okay. So for the pressure control, so we calculate it by the weight of typical passengers, and we get 4.9 kilopascal. This also below 30 kilopascal threshold. And also we are maybe we are going to monitor the area of the pressure by X sensor or that scan. So we target SPD below 50%. Okay. Okay. Next. So this is design analysis for vibration learning. What's important here is that this is our derivation, and then we get from this equation we get K stiffness, stiffness, and we have rated the thickness. Okay, sorry, thickness. So as you can see, this is very thin. So the visibility region is very high. So we can play around with that. So the target frequency as advised by ISO 261, we need to reduce the frequency because it will affect our body, and the region of frequency of the C vibration is 2.2 to 8 hertz. Okay, so this is a visual of body prominence.
Done. Next slide.
Okay. So this is okay.
That one, is that what is that? Oh, this is the front. Okay, next one.
This we will also discuss.
Okay,
And then
next one.
this is our evaluation. This is Dr. Zaki Salvini, occupational safety educator.
Okay,
Then that's all.
alright. Group 6, huh? Okay. Okay, let's go from the beginning. First slide. Okay, so this one for the solution for whom? For the taxi driver.
Yes.
Okay, so why you have this? I get like a Malaysian professional driver. I thought like a keep it simple. Malaysian taxi, e-hailing driver. That's it, done. Because that's actually what you users specifically for that one, right? So professional there, and then commercial drivers. Commercial what? Is it like also big trucks, also commercial, right? I don't know. So don't confuse. If it is for taxi, taxi. That's it, done. I mean, straightforward. Okay, that's the something came to like this. All right. So here we have this back pay, etc. Okay, go after that. Solution right away. So here, so what you need? No, this is to start from the solution. What is the problem user needs?
Provide numbers what?
User needs. User needs.
Yes, sir.
What is the problem basically faced by?
Sorry.
Okay, so pain relief. What is this pain? Pain is coming from, what are the problems first? Let's understand the problem.
Lower back pain.
Lower back pain. Okay, anything else with this taxi driver?
And also muscle sore.
Muscle sore, okay.
Posture.
Okay, so these are the issues, alright? And this, they will cause what? They will cause this, pain? Pain where?
The lower back,
The lower back?
neck, and also the muscle sore because
Okay, so now why then the user needs become, okay, pain relief? Okay, maybe I can understand. Right. Pressure control, what is that?
for muscle sore.
So he wants, the user needs, he wants to have pressure control.
They want the pressure of certain point is okay for every part. So that's why we come out with bone inconvenience support.
This degeneration protection?
So this is not from user needs. We get it from user needs, but because they feel the vibration of the driving, so they assume that it's affecting their health. And it is also backed up with research.
Okay, anyway, like I said, I'm not, but assuming, I don't know, you have to maybe do the word, but let's say for pain relief, then, now we want to relieve the pain on the lower disc, you said, right? Then you have your target for that, engineering 100 to 200 millimeter range of the height of?
The height of lumbar support. So, our concept is that maybe different taxi drivers have different height of the lumbar.
How the height, that height will reduce the pain?
Because it follow the spine alignment. So we need to make sure for example, if I put lumbar height at this maybe too high, so then still hurts. But
the height of what? What are you putting there to reduce the pain?
The lumbar support itself can be adjustable.
So we're going to put some cushion basically here on my back. And that we think by putting the cushion, I tried many cushions, didn't solve my problem actually. But anyway, okay. So you put the cushion there, then I won't have pain. Is that what you're saying? Okay.
Cushion is adjustable.
Yeah, adjustable according to their comfort.
The cushion.
Like I said, if I put cushion, I put pillows, I put things. I think it's not helpful, but maybe not the right. Anyway, then support pressure, 10-15 Newton. What is that for pain relief? How does that relate to pain relief?
so we need to make sure the cushion is gives the right amount of force. Right? So if it's too stiff, maybe it hurts. If it's too soft, maybe it does not have enough support.
So how is the pressure coming from the cushion? Is the pressure coming from the cushion? The 10-15?
sorry, I cannot answer because the accent did this, so yeah, maybe I will ask later.
No, because they have to match. That's my point here. Pressure control here to pressure what? Even pressure distribution on where? On no, the back, the legs where?
The base.
The base. So I'm sitting on it. This one, give me the pressure, right on the bump basically. Okay, maintain surface pressure below 30. Why that 30?
Also, done by 200.
Oh, that doesn't work like this, you know.
Didn't communicate with each other.
Okay, and then attenuate vibration amplitude by 50% at 4, 8 range. And how is that again will vibration definite? Is the disk degeneration coming from the vibration?
Yes.
Okay, and then they found if you reduce the vibration whatever by this, then you don't have that. Based on article.
And also
Medical or standard or whatever. Okay. I'm not sure about some of them, but let's say, okay, now go to your first your system. I want to see your system. No, the drawing of your system before the design analysis. Okay. So what are the components here? Where is the dampening?
So the dampening is only from the material. So we use high damping EVA foam pad, and silicone gel is for body firmness pad.
Okay, what is that one? So this one is a movable thing, right? So I take this one and I install it on my current car chair, right? So I just attach it there and then I remove it, etc. Right? Is that the idea? Okay. I'm not sure that two chairs in the chair, right? Okay. Anyway, assuming okay. So you have the dampening system, then you have the question. What is the question that you talk about? The question that you put on the lumber, the highest. What is the question? The medium firm foam. Okay, then you call the question here foam. Okay, fine. And then lumber support.
Yes. This is but
I want to know how many components you're going to design. So you have the dampening evaluation.
1, 2, 3,
And medium foam, right?
Yes.
No. Silicone gel, what is that?
for body firmness pad for body.
Is it a component?
Yes,
What you're going to design. So you have 1, 2, 3, 4, 5, 6. 3 and 3 there.
5. 1, 2, 3, 4, 5. This is the same.
Those are the same as this?
Yes.
You're going to use the same on the bottom, same on the back?
Yes.
But it's not the same. What you have, this you want to give some pressure, this you have to give something else? Is it the same like for my back or for my, I'm not sure, the requirement, is it the same?
Yeah. We put it as the same.
Okay, let's assume the same. So you have basically what? 4 then? Because here given the height, the length, the thickness, they shouldn't be the same. Because this one should be higher than this one. You know, you can see this and this. But you say the material, whatever, everything the same.
Even from the CAD model, you can see it's not the same height, right? Same length.
Oh, really? This and this.
So how come they can be the same, the design-wise? Anyway, let's say now we have 4, okay? Let's say 4, not 5, not 6. Okay, now show me one simple design analysis for one of them. And then we'll see if it is correct or not, and then we go to the other. So here, what are the designs? Which one?
The number height. This to this. So we aim for.
Go back to the 3D and tell me which component. Which one?
This one.
The small one. That one, the medium fill form. Okay. And what is that one in the chair?
this very close track, so actually, like I said that, but I'm not sure.
So the medium firm foam is the stripes? No, I thought this one that you designed, the medium firm foam, is it the stripe? No. It's the middle of the chair, right? Ah, that one. Okay. All right. Set the all right. Now show the calculation for that one. Okay. What is the design, the engineering target? Use it here.
Provide support of 10 to 15 and also adjustable height 100 to 200
Okay. Go back to your engineering target. I want to slow. Yeah. So which one? The first one.
Yeah.
The 10 to 20 and the 10 to 15. Okay. Go. Explain now. So what is the 10 to 20, for example?
So yeah. So this part, this focus on the height. So the typical about height is from 530 to 650 millimeters. So we calculate it, and we get it is adjustable in 10 centimeter range. So
No. What is the 200? You said you want to have the range from 200. What is 200 to 400 to 300? The engineering target.
that is only the adjustable part, meaning that
But you put it as engineering target. That means you have to use it for your calculation. I don't.
oh, okay. So the difference between the 300 and 200 is 10 centimeters. So we can adjust it by 100 millimeters.
This number here, how did you calculate this? 530 by 40 over, that's for 40%. Okay, this one for 50%. No.
This is from article with percentage of 40% from the seat to shoulder is 40%.
Okay.
And then 530 is typical from brackets to shoulder. So we assume this is different percent and then this is different percent.
Okay, so this is for shorter one, for taller one.
Yeah.
So you find 212, 50, 10. What is the conclusion?
So the conclusion is we can adjust it by 100 millimeter to for both seat, for both users.
So the range, you mean the range?
Yeah.
12 to 310.
Yeah. So the range is 100 millimeters, so it can as the user needs. So basically the user need should be only 100, not 100 to 200.
Okay, I still don't get what is the engineering target there. If you go back to the engineering target there,
Target.
go back to the engineering target, please. Yeah. So what is this 100 to 200 millimeter range? I mean, where is it used in your calculation? You just say, okay, if I take the shortest guy, whatever average percentile, this percentile, then it is 100. Okay, so 100 is there in that range, so it's okay. That's not the design we want. So if you want to do this, again, this one should be the one that you start your calculation with, not just to verify if it is done it or not. The same, I think, for the other one. Because here, if you have height adjustable within 100 to 200 range.
The range? Oh, yeah.
Yeah, for this one. Like I said, it's not, because what you're doing is the analysis type of design, which I said don't do that. So you calculate and you say, okay, it fits my calculation, then it's good. It doesn't fit, then let's try again. That's not it. I should start from the target and then define my spec. Anyway, for the other one, 10, 15, also the same, I think you did. You just calculated, go back to the calculation. So you have, I don't know, this force over pressure. What is that? F over A? Which F, which A?
A is the seat.
So now you're not doing this one, you're doing the bottom one.
Yeah.
But I thought this component is the...
Okay, sorry. This is the A is now.
So where is that force coming from?
Force coming from the support.
What do you mean support? How did you get this 10 Newton, 15 Newton? You started with it, and then you divide by area. What is the area? 0.15 millimeter square. What did you get then?
It's the contact surface area where the back touch the lumbar support.
So you assumed that contact, or what is? How did you get that area? Because what you're doing here, you're not doing anything. You just took 10 divided by area, this divided by this, so it's below that, or than 30, then it's okay. Again, that's not the design. You need to design this part, right? This foam. I want to see that foam. For example, is that area 0.015 millimeter square the area of the foam? Huh? No, the 0.015 millimeter square. What is that area? Contact surface. What do you mean contact? So contact between?
Yes, this area. Contact.
Your design is not so.
I think that it mixed up. I think what you need to find is the area that should be supported by the normal support. Whether it can achieve the minimum force that can be applied to your back. But it seems like you have given some area.
Because from here, I mean, how did you choose? How are you going to choose the foam? That foam, how are you going to choose it? After your calculation, how are you going to choose it?
Maybe from the stiffness.
No, I mean, this one you said for that 10, 20, 10, 10, whatever it is. So now you have to get that foam to make your prototype. How are you going to buy your foam? What is the characteristic, what is the thing to get your foam?
So I suppose we should find the area. No.
I don't know. Area what? Something that related to the foam. I'm going to go to the guy now to buy this foam to make my chair. What do I tell him? Just give me a foam? You know? The thickness of the foam, I don't know, the material of the foam, the whatever the foam. How do I know? From your things here, there's nothing to tell me. I found some characteristic of the foam here. Something related to the foam. The damping, whatever it is. I don't know what property of the foam is. Material, something. Area, land, height, the thickness, something. I don't have any info about my foam here that I'm going to buy, and then I'm going to put it and build my chair. That's the point of the design analysis. So to start from the engineering target and find the specs. So now, if I want the foam, I will go, okay, give me a foam that has this length, this height, this thickness, whatever this, I don't know, damping coefficient, whatever it was. Okay? Then he would say, oh, this one will suit you, this one, whatever. Same for the other component. It's not like that's here, I put area verify, okay, everything meets my target of something like, I don't know how, right? And then, if I make my prototype, nothing to do with my calculation. Understand?
Yes.
So, you have to do your things, either you design number or double verify those, and then make sure that it will match actually Starting from that, you get some specification of the component that you want to buy. Otherwise, give me a foam, give me a dumbbell. Can you go for another one? I think the other one is here, if I'm not mistaken. The dumbbell or something? Vibration dampening here. Because of this, target frequency 3 Hertz to avoid spine resonance, based on ISO or whatever you got, right? So here they say what? 4 to 8 Hertz? Okay?
What? 4 to 8 is not okay for body, pure for human body.
So it has to be below?
Yeah.
Or above?
Out of that. Yeah.
Out of that range. So either less or more, but not 4 to 8.
Yeah.
So you decided to get 3. Right? Out of that. So that's your target. Okay? And then this one, to align with my lead taxi vibration, 2 to 8. So how come here now it becomes 2 to 8? The second one is 2 to 8. So 3 is there.
So the range of vibration for delta with for different speed is 2 to 8 hertz. And then some of that clash with human body damage, which is 4 to 8.
4 to 8.
So acceptable is that we can go out of 4 to 8 range, which is 3.
But it will be in the 2 to 8.
Yeah.
So that's
2 to 3 only.
Huh?
Only 2 to 3.
Understand. But the first standard, the second standard, or whatever, or the second paper, that's not contradiction, but the range is different. 4 to 8, the first one.
4 to 8 is for both. Okay, the 2 to 8 is the range within the car, and 4 to 8 is the range which will cause harm to the human body in general, not in car.
Okay, so for car is 2 to 8, is it good or not good, that one? Or whatever, or that's the vibration coming from the car.
Yeah.
So that means that 4 to 8 is within that range.
Yes.
Okay, so if you put 3, then it's not good. Or is it good?
It is good because it's out of the.
Oh, it's out of the 4 8. Okay, I understand. Alright, so you put 3, right? Then you start with what? 3 hertz, then I don't know, that's an equation we have to check later, right? And then you find the stiffness. This is of the foam, right? Or something like that. Huh?
Yes.
But that equation is 1 to pi k over 30 kg. What is 30 kg?
The 40% of user body weight. This is not. So when in seat, we only use 40% of our body, 40% mass of our body.
Which one? Are you talking about? This foam now, right?
Yeah.
This foam. The bottom one. So when I sit in it, only 40%.
Yeah.
Well, what happened to the other 60%? Oh, my legs are very heavy. Okay. Anyway, assume we'll find. So that one, so you get that. Okay, this, and then you get that one. I'm not sure. Again, the equation, vibration, maybe, I don't know, just a bit of whatever vibration can check. Right? But at least this is the right approach.
Okay.
Your engineering target is 3. And then you find the stiffness of the foam. So now you can go give me a foam that. But here, again, for the foam, you have to decide the dimension, right? But that one you can fix it. Depends, but you have to fix it on other requirements. You don't make it like too high, then he will hit his head. I don't know. There will be some other requirement to find maybe the thickness of the cushion, etc. And then you find like this, for example, then I need this thickness, this size, this stiffness. Then I define my foam. Okay? So you try to similar kind of to this one. So now in your engineering target, you have the 3 hertz, right?
Yeah.
Can you go back to just that one and then I stop here? Already we have too long. Engineering target. Just to double check that 3 hertz, what is it?
So we need to get out of the range. So our target is 3.
At 4, no, at 28 vibration amplitude by 50, at 4 to 8 hertz range. No, not at 4 to 8. You said out of that.
Oh, yeah.
Yeah, out of the for 8, and then you put 3 in your case, right? Or then actually here you can just put the engineering target frequency 3 Hz, and then you explain. Alright? And then you explain why 3 Hz, because 4 to 8 will cause damage, so out of that you explain what happened. But your target is 3 Hz actually here. Okay? You do the other the same. So whatever you put that number, you should start from it, and then you find some spec of the component related to that. Similar to what you did for the dampening. Even though the dampening is not complete, because you have this,
Yeah.
not only the stiffness, I need to have the dimension here, maybe the thickness. You can fix some, maybe the other to be the same size of the cat seeds, right? But maybe the thickness will be the other parameter you need to find. Okay? Alright? Thank you. Finish up. Oh, huh? Yeah, but still okay. That's approved. Right?
We need to understand that, but we can have no issues. It's up to you.
Try to make it short.
Okay. You have 7 minutes. Your time. Okay, your time starts now.
Alright, with group 2, Razi, I'm going to present as Felix, a role rehab solution for receptive patients. You skip one. Most rehab centers are in city locations, they're in urban areas, and so rural people have less access to it. So we're trying to enhance and enable them to gain access to reliable risk rehabilitation at home using specific devices. This rehab can be time-consuming and expensive, and this physiotherapy needs to be more accessible. And the main indicator for this is that the ratio of physiotherapists to patients in this country is only a quarter of what's recommended by the World Health Organization. Next. So this is benchmarking. We try to see what's already available in the market. And so you have the official devices that can be sold, and as you can see from the price tag, it's about 370 ringgit. So it's costly. It does not have as much adjustable resistance. It's not really portable. As you can see, it's pretty bulky. And it's very difficult to produce, and it requires a lot of intricate parts to it. And it does provide some injury protection. The basic dumbbells, which most people are aware of, you have them. It's pretty cheap. You have some very little variability because it's in half kilogram increments and so on. But yeah, this is just a quick overview of benchmarking. Next. So our design idea is needs to be a modified constraint induced therapy and so on. These are just some quick infographics about it. Go ahead. Go ahead. So this is the standards that we need to follow, and this is what we base a lot of our engineering targets from, which is the Medical Device Authority of Malaysia, which is under the Ministry of Health Malaysia. And it does need to be classified as an upper range of motion exerciser, and it needs to be under Act 737. Next. The first use we need over here would be it needs structured incremental exercises to rebuild strength, mobility of hand and wrist while preventing future injury. So what we need is for the device to be rigid, durable, and include variable resistance. The engineering Oh. But yeah, mainly the engineering targets, this is not this one, the combined stress comes from the weight, the average Malaysian weight is 65 kilograms, and about 10% of that goes to the arm, and so it's about 6.5 kilograms that should be, that's what the device needs to withstand, and that, based on that, and also the dimensions of the forearm, the average dimensions of the forearm, we were able to get a combined stress. Durability, we calculated basically how many, based on the exercises, the amount of sets or repetitions, and how often do they exercise over the entire exercise period. We were able to get about 50,000 cycles, and that's how durable the hinge needs to be. And then the variable resistance based on specific exercises and recommendations from the physiotherapist interview. It needs to be a increments of 10%. That's the resistances, and it needs to go from 0 to 95 newtons on the band. Go ahead. From the second user need, we need to address the stiffness of scar tissue without aggravating pain, which is basically trying to increase range of motion in two dimensions, which is this one and also this one, as you can see at the bottom. And for that, we do need to be able to measure and display the degrees of motion in both axes. And so we need it to be from a negative 90 degree to a positive 90 degree and have an accuracy of about 0.5 degrees. Next. This is the user needs because it's specifically to rural patients. It does need to be accessible and affordable. And so we're aiming at a cost under 90 ringgit and a compactness that can fit in the regular standard backpack so that you can quickly, you can move it around very easily. Next. The safety to use, this comes from the medical authority that we discussed earlier. The material safety, since there's going to be some material in contact with the skin, it does need to follow these parameters. So, and also it needs to also have a safety factor of 2, and same with the agronomic safety and so on. We have a bunch of safety guidelines for us to follow for the design. Next. So design calculation, I wrote that.
Okay, so for our design calculations that we have how for it to be safe, we need to know that the resistance provided by the band have to be a certain forces. So from it we get what is the average force or torque created by the wrist for a normal healthy human. So basically that's the max one. So from there we got the 13.7, 13.5, and from there we took the highest maximum, and then from the top we get that the force that normally exerted by healthy wrist is around 90.11 Newton, and then and so from normal static at the maximum position we get the resistance of the band, which is the tension, is around 55 Newton, so it's around 56 Newton. So we have to pick resistance band that is no more than 56 Newton.
Can you just go to the board calculations? Next. Next. Yeah. Basically, as I mentioned before, from the dead weight of the arm, we were able to get a distributed load. From the distributed load, we found the maximum bending moment due to that load, and then we also found the bending stress due to the moment mentioned by Afri. And so we combined that at the center of the board, so we can get a ratio between required yield strength to thickness, since we're still unsure about the thickness of the board that we're going to be using. So you might be wondering why we now have two unknowns. We're going to be comparing materials based on their cost, and for each thickness.
settle the problem okay, but actually the problem is not this, right? The problem is with the people that they do rehabilitation of their wrist. Okay? What are the problems that they are facing there? That's, I know this, whatever, that's physiologics. This is to show that you need a solution, whatever, you know, to replace physiotherapy, but that's not your problem. The problem, like, let's say now you have these patients, what are the needs that you have? So this is why I think here, in the problem statement, I think you should
adjust.
you understand, right? This one is like just the setup of the things, you know. We have less things and then you need to go to rehabilitation. But then, okay, but what is the problem with this? After, let's say I don't go on there, your solution, what is the things that they are facing, these guys, even when they go to rehabilitation? It's like to have the stretching, to do this, to do that, whatever. So again, I know what is the problem of the patient. Understand?
Yeah.
Okay. So this one, like I said, it's good to have it as a background, but that's not the problem actually.
Okay.
Okay. So the problem is goes later. Go ahead to your maybe design spec, I guess. Because the user needs are there, right? Okay, that's good. The one that you put the standard. All right. Yeah. So here you have this. See, like they need this. This actually the problem.
Oh,
Okay.
okay. So adjust that based on.
Yeah, because this, okay, they have the goal, they don't do it, but what is the problem? The problem is they have this. They need actually incremental things to rebuild this trend, blah, 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 etc. Right? Because that's what be related to your solution. Your solution is to fix this. Okay, so here we need the strap fine. This one?
That one actually is a mistake. I was supposed to add the mass of the average lesion and then the dead weight of the arm. We based all our calculation based on the dead weight of the arm.
Then you find this number.
Then we found it.
So that's fine. Okay, so we put that one. Your engineering target is actually, since it's going to support this, whatever, like, again, you go like the previous one, average, and then the hand will be 1 kg or whatever it was. And then you design for that. Okay, and the length, etc. So you get those are your engineering target. In this case, the second one, the life cycle. So this again, 4 to 6 sets of 8 repetition. So you did all the calculation. You found around 50,000 cycle per.
For the whole period of physiotherapy.
Which is?
About a year or so. We assume it to be 1 year.
Okay, then your engineering time should not be like that again. It's similar to the first one. Because like you don't want actually the machine to last only for, let's say I have for this, so I'm not going to use that thrower. So that is not used anymore, right?
Yeah.
So what is the better engineering target to be here?
Yes. Because we cannot say it to be lifetime. We put it at the time of physiotherapy, how long it takes for you to be basically fully recovered.
So how did you get that 1 year?
From what do you call literature review from previous physiotherapists.
After 1 year, they will get restored.
Yeah, the physiotherapy sessions usually last about 1 year.
Yeah, and then it will be restored, right? I mean, he doesn't need it anymore.
Yes. Yeah.
Most of the patients.
Yes.
Okay, you can put that one. Then maybe you can put at least for 1 year, and then when I ask you why 1 year, then you say this because this usually averagely takes 1 year from this rehabilitation to get that. And then from that year, the same as that one for the month.
Yeah, okay.
When you do, you need 4 to 6 times, blah, blah, blah.
Okay, so just mention the 1 year here and the calculation as well.
Or you can mention actually that one, 4 to 6 sets of 8 to 10 repetition for 1 year.
Okay. All right.
That's the ideal kind of rehabilitation recommended, let's say, by. From that, later when you do that one, what do you mean by 1 year, 4, 6, you do the calculation, you find you need 5,000 cycle.
Okay.
Or 50,000 cycle, whatever. Then you can use that one for whatever design that you need for whatever one. Okay? Increase resistance, I think, okay. I mean, try to, I'm not going one by one, but the other, make sure that they are similar to number 1, number 2 that we corrected. Right, okay. Now, before the calculation, can you show your system? Like the drawing all the components. I want to see all the components. Okay? So what do you need here, component-wise?
Component-wise, you need Actually, not leave it here. This is better explanation.
Okay.
We need the. Leave it as it's like the drawing.
The drawing. I want to see the system first, and then we go for one sample of calculation. Just to see that you understand how to.
Yeah, the two sideboards, the baseboard which your arm sits on, we're thinking of having a sleeve for stability, a foam sleeve that you put your hand inside, it can be rigidly attached to the system, the handle and the resistance bands.
So this one you have to attach them, the system?
Yes, yeah. Because we're trying to make it so that it's collapsible and then
Good, I know that, but is it better not to do the mountain every time but still be collapsible?
It's like foldable.
Yeah, foldable. It will be nice. Because like this one, I mean the user has every time to do and maybe he doesn't know or not really handy, whatever. But he has to, okay, put this, attach, do,
we don't mean
just
it
like, just open, put the thing, then fold it.
Yeah, we don't mean it's right for you to have to do it every single day before every single
Yes,
exercise.
still, it doesn't look.
Okay.
You know, like you say, you put this in the market.
Oh,
Who's gonna buy 5 pieces of that assemble every time, you know? But if you get that one with some hinge, let's say, whatever, then
we're also thinking about reducing like labor costs because that would incur labor costs and add it to the cost.
I mean, what labor you're gonna make instead of putting that one and put this one, make it a hinge and this one permanent. But that hinge it will like a door. Do like this, then close. Do like this, it locks. Hinge. Simpler and actually more, I don't know, ergonomic or professional, whatever you want to call it, right? Because here it doesn't look, you know.
Yeah, I understand.
So that's my point. Okay, so maybe we can improve on that one. Okay. Then it will be foldable and easy actually.
Okay.
All right. So you have this 1, 2, 3 boards.
Yes.
Okay, and then
the handle, the dowels, which will go into
handle. What do you mean? That the one. Okay.
The part that you the swivels.
With some hinge or whatever.
Yes.
Right. Okay.
The rubber bands, we call it the securing method, whatever foam that we put our arm through to secure it.
This one.
Yeah.
Okay.
We're still, it's either this or straps, so we're still being.
There's no more time to think about solution. You should have made up your mind by now. You don't design analysis and go for prototype. Anyway, okay. Next. Next. Maybe one example of. Actually, your bill of material or bill of process, whatever you have. Just to see how many components. All right. So you have resistance band. Which one? This one is the one.
The rubber bands.
Huh?
The rubber bands that we attach to the sides, it can have resistance.
Okay.
Go back to the design.
Of the shells. Okay, it's okay. Clamps or strand band. This one.
This is the sleeve you put your arm through to stabilize it.
Okay. The wooden dowels.
It is the knobs that you put to the side boards that you can attach the rubber band to form the resistance.
The wooden boards. The one side.
To the side, yeah.
The foam padding.
Foam padding. It's in case that we're not using the sleeve, we put the padding.
What happened to the handle? That one. It's not there, right?
It's not there, no.
Okay, that's right. So you have this one plus the handle, right?
Yeah.
Are we missing anything? The hinges.
The hinges as well.
You have to have the hinges. So you have to design that. All right. Now show me one example. Again, you pick the example. You have many. You pick one that you started from the engineering targets, and then you did whatever your calculation, and you find the spec of that component. Show me one example to see that if you do it properly or not.
We'll go to the baseboard calculation before the simulation.
And then we finish here, and we don't go to
And this one, yeah.
Okay, let's see.
Basically, it was
Before next time when you do drawing of the components you're trying to design.
Okay.
If it is the handle, you put the handle, for example, right? So then we know this related to one, okay? And then you put the handle, this is the length, 10 millimeter. This is thickness unknown. And then based on this, you find what is that unknown. Then it will be,
simple.
okay.
Yeah.
All right.
This
So
for the
for
baseboard.
this one for?
For the baseboard, you put your arm on top.
The board.
Get the board at the bottom, and you put your arm on
Okay.
top. We start with distributed load, which is basically 6.65 kg, which is the weight of your arm from the shoulder to the fingertips. And then we got basically distributed load, how much it's the load by length of the board.
Okay.
From that, we got the bending moment due to that load.
No, wait. So distributed load, that one? 6.65 by 9.8, so that's a Newton. What is the 45?
Length of the point in centimeter.
Oh, the length, okay, fine.
Then we got the bending moment due to that.
So the length, you fix it?
Yes, it's based on the forearm, from fingertip to forearm length of the average relation.
Average, so you put it fixed,
Yes.
okay, fine, alright.
We got the bending moment due to that load, and then we have a second bending moment due to the hinging action when you're doing the exercise. And that comes from from the rubber band calculations that we got, the 65 newtons for tension and compression. Basically, it's the bending moment due to the exercise.
Okay, that one we have to check later, but okay, let's say, keep going.
And then we combined both of those to get the maximum normal stress at the top center, basically the maximum normal stress at the middle of the board.
Okay.
And then from that we get the required lead strength to thickness, since the thickness is also we're not really sure about of the board.
The thickness of the board.
Yeah. So basically we have these two variables to play with, and we'll choose based on the cost. So some materials, the strength to thickness ratio or something like that, we can play around with to get the cheapest cost.
Alright, so what is the outcome now?
The outcome is the yield strength to thickness ratio, essentially. So basically the sigma ultimate to the thickness that we can get from that material. H is the thickness.
Why you take sigma, the ultimate or the?
Based if it's wood, then we probably use yield, or if it's a ductile material, we use C yield.
Design wise, you don't use one. You know what you mean by ultimate? Ultimate is maximum strength.
Yeah, but some materials, since they don't have any yield portion, so we use the sigma ultimate.
No, that's for brittle material. That is also still ultimate yield is the same because they don't have plastic region, right? So that's the maximum stress. But you don't design for the maximum. The maximum is like the break and one.
Yeah,
so very close to break.
And of course we have a safety factor of 2. So
that's why. So instead when you use safety factor of 2, instead of your SY, you use SY over 2 equal to that one. And then you're done with your design. You don't design, never will design for SY or SY fail.
Yeah.
Mechanical, SY is fail, even though it is still before the classification, but that's failure by yielding. So that's why the factor safety, what does it mean? That means the operating stress is half of the yield stress, that's your 2.
Yeah.
Right?
Yes.
So if you say that one, I'm designing for, I don't know where you get the factor safety of 2.
From the standards that we use.
The standard, exactly. So if it is that's your target, then here you have SY2 over 2.
Yeah.
Then SY2 over 2 equal to this one, right?
Yeah.
So what is your material?
We're still choosing based on what's available in the market. Since the cost it's based on the cost essentially. So whatever is cheapest in using this ratio.
What material? Aluminum is very cheap. Whatever. What are you looking for? Metal? Not metal? Plastic?
We're looking mainly for plastics. So.
Plastic also very cheap. You can even make for different stuff. Anyway, no. My point here, you cannot. So like this one. That's why I said, what is the outcome? So after this, what you gonna do? You're gonna try material?
Yeah, try materials and thickness. Like basically, since we have 2 variables, the stiffness and the.
That's why you have to fix something. So fix the material.
Fix the material and design based on the thickness.
Yeah, based on the medical, for example, what is usually recommended? Is it plastic more or metal more or I don't know what, foam, whatever it is. From that stand, maybe you can find for these devices usually what they recommend kind of the material. So if it is poly, blah blah blah, polymer, whatever, then you say, okay, I'm picking the same polymer that they make some other medical devices from it. Then you get what is its ultimate strand. You replace it there over 2, then you find the thickness. Then you determine the thickness of your blade. Since you fixed the length based on the length, the material based on the standard, what left the thickness, then you get the thickness. So then it will be correct. This is what I want.
Oh, okay.
We want you to do similar to this. Again, I have question. Here I didn't check. I'm not question mark, but I have to check because you added many stresses. I have to see the other one if really related with stress involved with this calculation or not. Then you have to double check later, right? Okay. But let's assume that it is correct. So you started really from the weight, right? Which is your engineering target. You find blah 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 and you fix it something which is, let's say, the material, then you find that you fix it the length based again not like arbitrary, but based on the length of this, which is good, then you deduce the thickness. All the other components has to be the same. Engineering target, blah 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 calculation, whatever. If you have to fix something based on standard or whatever it is, or the Malaysian population, whatever it is, the user, then you keep one unknown, two unknown, depends how many equations you have. If you have one equation like this, you keep just one unknown and you divide.
Okay.
You deduce it. Alright?
Yes.
Then it will be, that's what expected from your design analysis. Alright?
Alright.
Okay, thank you.
Thank you very much.
So he's done. Okay, I told him he would finish early, but he's happy with this time. Alright.
Alright. Congratulations.
But you don't have no more like still thinking, huh? You don't have much time, huh?
Minutes on the side.
Yeah.